My name's Cooper, and our group made a steganography tool. Our goals for this project are to upload a base image, which is the dog.png, and then to upload one of the 10 hidden images that we have, both of which are 400 by 400 pixels. And then using one of the embedding techniques we created, we're going to embed the hidden image onto the uploaded base image. And then we have buttons that allow us to recover the hidden image, as well as output the resulting uploaded base image with the uploaded hidden image embedded onto it. And the code I wrote for this is the function to flatten the image. So what it takes is it takes a gray image input, which is the hidden image, and it takes some threshold, which we just defined as 128 here. And what it says is that for any pixel in the gray image, if it's below the threshold, we're going to give it a binary value of 1. So that means all black pixels become 1, and all white pixels become 0. Now, taking this binary image, what we're going to do is we're going to expand the flattened image into an RGB image. And all this means is that instead of having logical 0 and 1s, we're going to be setting a value of either 0 or 255, where 0 is black and 255 is white. So we take our RGB image, and we're going to make it the same exact size as our binary image, and we're going to set 3 color channels. We're going to be going through red, green, and blue. So as we go through these 3 color channels here, we're going to be saying that if the binary image is logical 0, then we're going to multiply it by white, and we're going to be setting it to 255. And then if the binary image is equal to 1, then we're going to be setting it to black, which is 0. And all this does is create 3 2D matrices where it's either a 255 value for a white pixel or a 0 value for a black pixel. And all this does is create 3 grayscaled RGB matrices.
Hello, my name is Jacqueline Maya, and this is our steganography tool, GUI. So as you can see, it is very simple and efficient. It allows users to easily embed their images and be able to choose whichever image they like. So firstly, there's this upload base image button. So first the user clicks on this, and from there they're prompted to select any image that they'd like. So I'm going to use this image, and after this the image shows up here on this base image axis, so the user can see what image they'll be embedding the hidden image into. Then there's an upload hidden image button, and the user can choose any image as well. So now they can see the hidden image in the hidden image axis. And after this, the user can choose from this drop-down menu any embedding technique that they like. So there's odd, even red, odd, even
I'm William
green.
Chung, and I worked on the embedding functions for our steganography project. The goal here is to hide secret black and white images inside a normal-looking image in a way that's invisible to the human eye. We start with the red embedded function. The key idea here is to encode each pixel of the hidden image by adjusting the red value of the base image. So if the hidden pixel is black, meaning 1, then we can make the red value odd. And if the hidden pixel is white, meaning 0, then we can make it even. In the loop, we go through each pixel, and if the red value isn't already odd or even like it's supposed to be, then we change it by adding or subtracting 1 to match the hidden image, and we make sure to keep the value within the valid range for that. Since each color value ranges from 0 to 255, changing a pixel by just 1, for example, going from 124 to 125, isn't noticeable to the average human, but it does allow us to store the hidden data. This same idea is used for the green and blue embedded functions. Instead of modifying the red channel here, they apply the same concept to the green or blue channels respectively. So that means we can hide up to 3 separate images, 1 in each color channel, without visibly altering the original image.
And I created the recovery functions to the embedding image functions. So this is the code to recover an image hidden in the red channel, which is why I'm referring to everything that is in the red channel. I then initialized a 400 by 400 matrix of zeros, which would store the recovered data or image. This matrix will hold zeros or ones, which represent the hidden image. I then created a for loop that goes over every pixel position in this hidden image. This line then checks whether the red channel value at whatever position is odd, and it will then divide that value by 2. And if the remainder is 1, then the number is odd, and if the remainder is 0, then the value is even. And after, if the red channel value is odd, then that means that there is a white pixel in that position, and if the value is even, then that means that there is a black pixel in that position. I then did the same things for 2 more recovery functions, but instead of the red channel, I did it in the green channel, as you can see by the 2 here, and then I did it in the blue channel, as you can see by the 3. Thank you.